flag only. In 8085, this is the new flag which is introduced, right? So this flag, AC, auxiliary carry flag, when this will be set to 1, it is if there is an overflow of a bit tree, right? So say for example, if you are going to add a number, right, something like A6 and 5F. So in that case, what happens is uh, you have to split that A6 as A and 6 separately. How do you write your A equivalent for binary is 1010. Your equivalent for 6 will be 0110, right? And similarly, when you write for 5F, it will be 0101 and all ones on the other half, right? So what I'm going to do is, if I'm going to just make an uh, addition of these two numbers, A6 and F5F, let me first look at 6 and F separately, right? So 6 is 0110 and F is all ones. So when you add them together, you will have a carry flag which is set to this, but this is not a carry flag basically. Okay, but that is a resultant carry which is available for the significant bit of 6 and F. Whereas the other significant bit of A and 5, when you do that addition, again you will have a carry flag. So the last carry is what is the result will be a carry flag, and the in between value, the addition of 6 and F has given a carry, So when this auxiliary carry flag will be set to 1 is when there is an overflow of a bit 3 of the accumulator. Normally you will have 2 bits in accumulator. So if the bit 3 is having an overflow, then you will have an auxiliary carry will be set, right? So these are the things which are the reference to the flags, right? Now getting back into the architecture part again to the next part, which we are going to speak about the program counter and stack pointer. Initially, I have been saying this program counters and stack pointers are again 16-bit registers, right? First, let us look at what is this program counter is all about, right? So this program counter, as said, it is a 16-bit register, and when it is used is whenever we want to send a 16-bit address to fetch an instruction from a memory, right? So when you want to, that's the reason. When you want to fetch a 16-bit uh, fetch a instruction from a memory, you will send a 16-bit address. Okay. So how this will act is this acts like a pointer, which indicates the address for the next instructions to be fetched and executed. Okay. So every time when this program counter is updated, after an instruction is fetched, so you will have the subsequent value also will be brought into the memory. Okay. Say for example, from a memory location of 2000, I'm going to fetch a data from there, right? And immediately my program counter not only holds the data of 2000, it also holds the data of 2001 also. PC plus 1. Okay, and similarly 2 bits and 3 bytes of instructions are also possible. Okay, something like PC plus 2, PC plus 3. It speaks about the location settings, right? Address locations. So just keep in mind your program counter is 16-bit register, which is the first point. Second point is it is used to send a 16-bit address to fetch an instruction from the memory. That answer show. That's the purpose of a program counter. Now looking at stack pointer, what this stack pointer is something like it is an area in the random access memory. Okay, in which all your temporary informations will be stored. Okay, and out of all the temporary information stored, you will follow the FILO basis, first in, last out basis. Okay, and how it happens is basically an address will be set in the RAM, okay, in the stack pointer, where the first information is stored at the stack entry. Okay, and gradually whenever you are picking up the data from that stack or the reserve pool area, gradually its addresses starts to decrease. Okay, so both are registers. Your program counter will have your data value, which is from a particular address. It will hold only the address only, not the data. Whereas your stack pointer, it is having it's a part of your RAM, and this stores again an address in the RAM only. Okay, so that's with respect to your stack pointer and program counter. Then you have got an address buffer. Address buffers are two: address buffer separately, address data buffer separately. Address buffer separately is an 8-bit, which is A8 to A15. Address data buffer is separately, which is AD0 to AD7. Okay. Then I said there is an ALU. ALU, or otherwise it is here in the block diagram, we have represented that as instruction decoder and machine cycle encoding, right? So that is your ALU. What this ALU does is it performs all the arithmetical logical operations. On the whole, your ALU will have the flag registers, temporary registers, and accumulator together, right? So this carries out the arithmetic and logical calculations of the data which are stored in the general purpose registers in the memory locations, right? And this arithmetic operations are something like addition, subtraction, comparing two numbers, incrementing one value to the another value, decrementing, finding the complement of one value or the other. So these are the few of the arithmetic operations that can be done. And logical operations, yes, of course, AND logic, OR logic, XOR, all this can be performed on the data or which are available in the memory. Okay, and all this result of these operations will be placed in the accumulator only. Okay, and if needed, we can also be placed in through the in the memory also through the bus which is available, data bus which is available, internal bus configurations, right? So that is with respect to your ALU. Then you have got a timing control unit which is available here. Sorry, which is your timing control unit. Okay, in this timing control unit, we have got two things, right? And instruction register and decoder and control signals. Control signals are nothing but the pins which are available here in the timing control block, right? When you look at the first one, X1, X2, which is on the left side of this, X1 and X2. This is your power supply, this is your ground, and this is your X1 and X2. Okay, what is this X1 and X2 are nothing but which is an externally connected to a quartz crystal. Okay, and this is mainly for getting a clock signal generated at a fixed frequency. We need a frequency of 3.2, right, for 8085. So that 3.2 is a frequency is generated using a quartz crystal, and that is connected through the pin of X1, X2. Okay, and that is with respect to X1, X2. Then you have got something like ALE, right? ALE something here. Address latch enable. It's an expansion of that term ALE. Okay, which is again a 16-bit, and this is basically divided into two. This mainly works on the address bus only. And then once when we said address buses, address bus separately and address data bus separately, each of 8 bits separately. Okay. ALE signal, what it does is it provides during the first clock cycle of the machine cycle, this address latch enable will be high. Okay, and when this is high, this will enable the lower 8-bit of the address to be latched either onto memory or to the external latch. Okay, so that ALE takes care of only that operation. Then you have got a pin like read signal and write signal, right? A read signal, what it does is which is an active low signal. Whenever you find a bar value, lengthy line above the alphabet, that means it is a low signal, active low signal. Okay, so you for read, for write, for memory, all these three pins you will find a line above that alphabet, right? So that means they are at active low. And whenever you want to perform some operation on that, when you want to read for some input from the other input device, then you will have to give an active high. Okay. அதே மாதிரி தான் you will have to do for write signal also. It will be initially at low. At times when you want to write the input or move the input to a memory location, then you will have to make that write pin, write signal W or bar to be active high. Okay. Similarly is the case for IO/M. Out of this IO/M to this pin, initially this pin will behave as IO only, input output pin only. That's by default. Okay. But if you want to move that pin to a memory variable, then you will have to make the transition from 0 to 1. When you make the transition, your IO will get as bar and M will get activated. So you can communicate with memory and your processor. Okay. And there are two status signals, S0 and S1, right? So based on this two status signal and the value of IO/M, input, output, and memory pin, from based on the signals on these three pins, your machine cycle is decided, right? What is my machine cycle is going to, whether it is going to fetch a opcode from, whether it is going to read a memory, whether it is going to write into a memory, whether it is going to read something from IO device, whether it is going to write something from IO device, and so, right? So based on this three status signals, two status signal and one IO bar M signal, your machine cycle operation is determined. Okay. Now coming to the next two pins of hold and HLDA. HLDA stands for hold acknowledge. Okay. And these two pins signals are mainly used in DMA. DMA stands for direct memory access. Whenever you are going to have a data transfer between your IO devices and memory in the microprocessor, this will be happening, right? So the involvement of the processor, what it does is it just slows down the data transfer between the IO device and memory. Okay, at that point of time, what you do is this transfer of data directly from IO to memory without involvement of microprocessor is called DMA. So that reduction of slowing down of processor can be nullified by using a peripheral called direct memory access. That point, what it will do is it will take care of that process of communicating between the IO device and the memory devices, right? So at that point of time only you will mainly use for the hold and the hold acknowledge signal. Okay. So what happens is whenever this hold signal is high, hold signal is having a value of 1, what it happens is the CPU will temporarily hold its operation. Okay. By doing so, what happens is the address bus and the data bus are now handed over to the DMA, direct memory access. At that point of time, the direct memory access will take care of the transfer of values from the output device to the memory. Okay. And once when the DMA controller has completed that process, for completing all your writing operation into memory, it will send a signal called HLDA, stating that whatever I was doing is over. Now, as a processor, you can proceed on with your work. So that is why your hold is towards, hold acknowledges outside the DMA. When you can look at the direction of the arrow mark, that clearly speaks about that. Okay. Is that clear till now? The pins? Yes? No? Heavy? Am I in the class? Yeah, okay. Am I audible? Hello? Am I audible?
Yes, sir. Yes, sir.
Okay, fine. Thank you. At some point of time, I need some inputs. And there is one more pin called ready signal, right? So this ready signal is an input signal. Okay. So how this pin can be considered as working is, at some peripheral devices, some peripheral devices like keyboard or some display devices, and any peripheral device for the matter, which is connected to the 8085 processor, operates at much slower speed than the processor. Okay. So at that point of time, what we need to do is we need to synchronize the speed between the CPU and the peripheral device. Okay, synchronize, either match your peripheral device to the speed of your CPU, or in other words, you can slow down your CPU speed to the level of a peripheral device. Both the ways are possible, right? So for that process, your ready signal is used. Okay, so if this ready signal is high, what happens is the peripheral device is ready and the processor can complete the data flow. If the ready signal is low, what it means is it is something like an instruction to the processor saying that IO device is not ready. So processor has to wait till that ready signal is up. Okay, is that point clear? Now again, there is two more pins available, reset in and reset out. Okay, so this reset in and reset out pin are mainly used to reset either the processor or the peripheral devices. Okay, the reset in pin may be low for operator reset button, and when this signal is low, the CPU will reset the program counter. Okay, and if that it also sends the high reset out, and if the reset signal goes to peripheral device to reset, from a reset out, all the processor peripherals connected to the processor will be reset on. When through reset in, your processor can be reset on. Okay, so this is with respect to the timing and control signals. You have got two more blocks on the top. One is interrupt control and the other one is the SID, serial input and data, right? So this interrupt, when I say, whenever you connect a peripheral to a microprocessor, at some point of time, this peripheral will try to communicate with your processor. So what it does is it sends a signal to the processor saying that I have a data with myself. I just wanted you to fetch the data and do some operation. So it is trying to interrupt that device. So whenever an interrupt is available, it will be available as such. We have got five hardware interrupts. So hardware interrupts are namely INTR, which is interrupt request, and there is other three hardware interrupts are RST 5.5, 6.5, and 7.5, and there is one more interrupt called trap, right? So these are the hardware interrupts. So out of this five hardware interrupts, the highest priority is given. The priority wise ranking is given. Trap is given the priority 1. That means it has got the highest priority, which is followed by with a rank 3 for 5.5 it is 4, and for the last one interrupt it is 5. So we'll come again on this interrupt as a separate part in the subsequent classes, right? So as of now, when you write an architecture block diagram, you will have to write the interrupt control as there are 5 hardware interrupts, which are namely INTR, RST 5.5, 6.5, and 7.5, and trap. So the following are the priority. Trap is with the priority of 1, RST 7.5 is the priority of 2, 6.5 with the priority 3, 5.5 with the priority 4, and INTR with the priority 5. So that is sufficient for your interrupt control. Okay. Now coming to the last block which is available there, which is serial IO control, SIO, right? Serial input output control circuit. Okay, so this is mainly used by the microprocessor for data transmission. Okay, and for this purpose, two pins SID, SOD are provided. SID stands for serial input data and SOD stands for serial out data. Okay, so this SID, serial input data terminal, this receives the serial data stream from an input device, the control unit, and then converts this serial data to parallel data before it is used by the computer. After conversion, that 8-bit parallel data will be stored in the accumulator for the ALU operation, right? Similarly, SOD, serial out data, outputs the 8-bit parallel available in the accumulator. Output accumulator enna irukko, adha vandu it will be moved on through the pin of SOD to the peripheral device. So one is input to the system, the other one is output from the system, right? So these are the 5 functional blocks which are available on our basic architecture of 8085 microprocessor is concerned, right? And next what we have is the pin details, right? So this pin details, I suppose, hello, there's an interrupt. Hello,
I think we can see next class, sir.
pin configuration. Okay. Okay.
Because
So
it's already 12:40.
okay, fine. So in that case, what we have gone through till in this classes about the basics of the process, classification of process, features, evolution of microprocess, and stepping into the configuration, and then into the architecture where we have got five functional units on the whole. The functional units are namely register section, arithmetical logic section, timing and control section, interrupt section, and at last serial input and output section, SID. Okay, so architecture wise it is over. So hopefully in the tomorrow's class we'll proceed on with or in the next class we'll proceed on with the pin details and the addressing mode. Okay. Um, so that's it for the day. Um, so the expected question from this part is the architecture part, and the part A question is concerned. You will have to speak about the terminologies which we used in microprocessor, and what we